For our next talk, we have Reetam Majumder, who's joining us from the University of Arkansas. He's going to be speaking on Vecchia Approximated density regression for intractable spatial extreme models. And before he starts, I do want to let you know that we have reached our quota on the number of talks that can use the quote, all models are wrong.
I have a quote, but it is a different one.
You're not allowed.
Yeah, thanks to the organizers for the invitation. This is lovely, and I'm sorry I'm late to the party. I feel like I missed some key talks yesterday, and the ones today morning have been fantastic. And I'm sometimes so siloed in my environmental stats workflows that it's interesting to see how some of this is being used in other fields as well. So this is work I did as a postdoc with Brian over at NC State and Ben over at CSU. We were working on streamflow modeling. We had the entire pipeline, like physical stuff with climate modeling, impact modeling at the other end, and smack in between was something which is not the physical sciences, which is just statistical modeling of extreme streamflow risk. So I have these two slides in the beginning kind of talking about the motivation of this. So these are two real events I'll talk about. This was in Vermont in the summer of 23, where I think 3 different rivers had rising levels, which led to a lot of flooding. And in that sense, that is extreme streamflow, and that's kind of what we care about. The other is a New England thing, which a lot of you might be even more familiar with. This was the winter of 2023, 2024, where I think, again, there were 2 rivers which overflowed, which led to a partial dam break and a lot of damage on utilities, on housing. People had to evacuate and stuff. And so that's why we kind of want to quantify the probability and magnitude of these things, especially at like multiple rivers and watersheds at the time, because that's how we kind of get an idea of how to prepare, how we can mitigate their impacts. So the data set we were working with throughout was across the US. It's called, it's a data set from the USGS. It actually goes far before 1972, and some of the watersheds are much, have a longer data record, but we were working with these 487 stations, which had a 50-year record continuously, because we didn't kind of want to deal with the whole missing data situation at that point. And there's one specific thing about these watersheds, that they were, as it says, minimally impacted by anthropogenic activity. So no watersheds near dams, no watersheds near, say, factories or cities. So whatever was happening was kind of like weather/climate signal coming through without human intervention. The plot here, the scale of the plot is kind of both relevant and irrelevant. So it's the annual streamflow maxima for every year. We have the maximum value that it took at each watershed. This is what we'll in extremes call block maxima, but we are showing it on the log scale, and we do study it on the log scale for some modeling reasons, which are not super important at this stage. And we plotted the 90th quantile over that 50-year period at every location. And so like the numbers don't really make a lot of sense in this situation, but you can see there is a fair amount of spatial variability across the country, in the coast and in the middle of the country as well. So the goal was, at every location, at every watershed, can we give what is usually called return levels? This is like the super baseline thing that extremes modeling kind of tries to do. More importantly, can we give joint exceedance probabilities? What's the probability that all 3 rivers will kind of overflow at the same time? Because that's where the damage, kind of becomes significantly worse. And finally, can we kind of test whether this has changed over the last 50 years of record that we have? A little bit of background, which might be familiar to many of you, but I still feel like is a disclaimer I need to give. So I love GPs. Everybody loves GPs. GPs are awful for extremes. Just by construction, they are good for means, not good for the tails. Not an analog, but the commonest thing for the sort of block maxima data we were working with is a spatial process called the max stable process. However, it's got 2 key drawbacks. The first one is the dependence type that it can kind of study is somewhat limited. Without going into too much detail, what this basically means, it kind of assumes that no matter how far 2 points are on that map, their extreme streamflow, so their tail values will be associated with each other, which is true for some physical processes in some situations, but for most physical processes like this is not a realistic assumption. Second, it's intractable for even moderately large problems. And it's like people who are familiar with Gaussian processes think a different number when I say this. No, the number I'm talking about is roughly 24 locations. Beyond that, the last time somebody kind of tried doing this that I know was in like 2015, 2016, and they like topped out, I think, 16, 17 locations. And beyond that, you start doing things like composite likelihood. So there are methods, but none of them are exact inference methods at that point. This is mostly for completeness. The very two things I'll point about. Just like you have Gaussian processes and normal distributions, in the marginals, we have something called a generalized extreme value family. For extremes, it's an asymptotic distribution in a sense that all maxima kind of converge to that if you scale it properly. And the spatial equivalent of that, or the spatial analog of that in this situation, is the max stable process. So these are the two things that I will be mentioning from time to time, and I just kind of wanted to give a sense of what they are. So for this sort of large spatial extremes data sets, because in the context of historical analysis, 500 data points is kind of getting there. We wanted a couple of things. We wanted a spatial process that was expressive and flexible. Expressive in the sense that I just mentioned, that the max stable process has certain limitations. What we do is we work off of an existing very well-known process called a Gaussian scale mixture, which mixes up a Gaussian process with some extremes component. The second one is what is somewhat more important here, is it's an exact inference is a no-go from the beginning, and we need some sort of simulation-based inference in this situation to kind of make that tractable. And in particular, I'll introduce something called the Vecchia approximation, which I don't know whether has already been talked about, which is a key thing in spatial stats that we will exploit. So my two collaborators on this, Brian, fiercely Bayesian, Ben, fiercely Bayesian. They like doing Bayesian stuff. And the model we kind of want to work with has this structure. We have our parameters for the marginals, theta1. We have our parameters for the spatial process, theta2. Generally speaking, theta2's dimensionality is much, much smaller than theta1's, and that's true for most spatial models that we have. The independence assumption I have between them is kind of crucial for this, but it also generally speaking holds in all the literature. And so if you look at the entire density of this, we need that likelihood piece if you want to do any form of Bayesian inference. If you do a change of variables, this is like intro to probability situation, you would decompose that into a product of marginal GV likelihoods, which you can fit or evaluate using base R functions. And that second piece, which is a vector of uniform variables, where all the spatial dependence is encoded. It's parameterized by a low-dimensional parameter vector. Now, it looks very similar to a copula, works very similar to a copula, just written down in this very classical format. And so if you want to do Bayesian inference, we kind of somehow have to evaluate that. As we'll see that second piece in there, the spatial dependence piece, that's what's intractable. And that is what we will attack. Just getting the marginals out of the way. The marginals will be GV distributions. We have a little bit more sophisticated modeling going on where we assume the parameters themselves follow Gaussian processes. All of this is very tractable. All of this we can do with very off-the-shelf MCMC. What's interesting is this piece. What we call the process mixture model, which is an extension of something called Gaussian scale mixtures that Husserl-Wadsworth paper had, is written as, you can think of it as a linear combination or an interpolation. It's not a statistical mixture in that sense. You're not choosing between the two processes there. You're always adding up their values at two locations. So the components are pretty designed in a very specific way. That R is that max stable process I mentioned, which is going to be intractable. The W is a Gaussian process, which we know how to work with pretty easily. The delta is a parameter between 0 and 1, which has a very nice property that because it's between 0 and 1 and the max stable and the Gaussian process have very different properties, around that 0.5 mark, their behavior, the extremal behavior changes. It's got a very nice interpretation. And as it says, both of them are on exponential margins because what happens is that if they are on exponential margins, the VS piece that's there, that's marginally hyper-exponential. So a lot of the math becomes significantly easier, and we need fewer numerical things in this whole process. But anyway, this is fairly straightforward to establish as an extension of the original process we were working off of. It's got some pretty nice properties, which some of them are shared with the original process. Some of the things like dependence dying out over distance was not present in the original process that we can have. However, the added complexity makes that whole likelihood intractable. We can't directly do inference on that for even a couple of locations. That said, it's very easy to draw samples from the model. So, do a draw from a Gaussian process, do a draw from a max stable process, sample a value of delta, and you have an evaluation of the entire spatial field. And therefore, we can do some form of SBI. Now, this is a slide where, like, most of the times I give this talk, I have to spend 5 minutes. But thank you to this crowd where I can just go over this in like hopefully a minute and a half. This is how most of, at least in spatial stats, how most people do likelihood, SBI, which is likelihood-free inference. Definitely the first couple of papers we started working off of, the Gerber and Nitschke paper in particular, did kind of that. Yeah, you have your parameter vector, you generate a bunch of values from that. We don't call it a prior, we call it like the design distribution, so to speak. It will usually share its support with the prior. Generate a bunch of values, generate a bunch of data, take some functional of the data and learn a mapping from that to the parameters, where the loss function is usually something like mean square error or whatever. And eventually you have a pipeline where you have your data, you plug it in to that network, and you get out an estimate of the parameter. Uncertainty is usually through bootstrapping, or in things like neural Bayes estimators. If you make a few more assumptions, you can think of the posteriors. You can think of the estimates as draws from the posterior and have something slightly more sophisticated. As I mentioned, we don't want to bypass the likelihood at all, which comes with its problems if we don't bypass the likelihood, but we do want to keep the likelihood. Because as Joel mentioned earlier, if you have the likelihood, you can tinker with things like the prior. You have access to more machinery if you can somehow approximate that likelihood. And that's kind of what we do. Here's my quote, is the simple way to do it is just take that little piece that had intractability, replace that with a neural network to kind of get an evaluation of the likelihood. Because we just need, at the end of the day, a scalar, which is like, if you think of it in a simpler case, it's like a D norm sort of situation. And if you have that, then the rest of it is very tractable, very compatible with just very conventional Bayesian inference. Ideally, this is the pipeline we want, where we plug in that vector of uniform values, which is going to be spatially dependent. We plug in that low-dimensional parameter vector, and we get back an evaluation of that f given u2 is that second piece in there. And if we have that number back, then a lot of machinery becomes accessible to us. Now, this is a couple of problems here. I mean, theta 2 is low dimensional. It can be high dimensional. This is not a bottleneck for us. It only means that if theta 2 is high dimensional, we'll need more and more data for this model. But since we're not predicting theta 2 directly, that's not a problem. The problem is U is high dimensional. So estimating the likelihood of a high dimensional space is not really going to work, even if we have a neural network. We do need to break this down into something low dimensional. And that's where the Vecchia approximation kind of comes into play. Now, it's a fairly simple concept, and it works for a bunch of things. And it's defined for any joint distribution, but it really shines for spatial stats. The idea is simple. I have 100 randomly sampled points in the unit square. First step, you order them. Not super important now how you order them. In this example, they were ordered by the Euclidean distance from the origin, bottom left. And once you do that, Bayes stats tells you can write the joint distribution as a product of univariate conditional distributions in there. So for example, on the left panel, the blue point is point number 11. You're saying that it depends on, obviously, the parameters which generated this entire spatial field, and also the values at those red points, the 10 previous points. Now, if you go up to, say, location 45, which is the blue point on the right panel, sure, it can depend on the previous 44 points, but what the Vecchia approximation tells you, that if you order well and condition well, it only needs to depend on a finite number of previous points. In this case, I just chose the 10 nearest neighbors. Nearest neighbors are usually the common way to go. It's not the only way to go. There is a broader discussion on how to do the Vecchia approximation, and that definitely affects things. But kind of works for most Vecchia approximations. Like, there is no version of the Vecchia approximation which will like completely break the model, which is kind of what we do. Oh yeah, so before I move on, what we suddenly have going from the left-hand side to the right-hand side, we started with a high-dimensional likelihood. On the right-hand side, we suddenly have a product of univariate conditional likelihoods. These are pretty simple. I mean, you can try to model these maybe using a mixture of normal distributions, right? Fit a neural network where it predicts out a mixture of normal distributions where maybe the mean and variance depends on those parameters, which are the input. We do it slightly differently. There's this thing that my Pierre Brand and one of his students developed called semi-parametric quantile regression for conditional density estimation. Idea is very straightforward. We don't want to use a parametric model to do that conditional density estimation. We just have a spline representation of that. So long story short, I mean, this looks more complicated than it is. Those BKs are basis functions. They are a specific class of basis functions, which makes life very easy for us because they are functionally equivalent to PDFs. And those pi's are a probability vector, essentially, that the neural network will spit out using like a softmax output layer. And so you essentially have a linear combination of PDFs, also going to be a PDF. And so that, if things are smooth, which it is in this situation, it can, generally speaking, estimate any conditional density that's smooth in its arguments. So the way this neural network works is in the next slide. Yeah, there we go. So that's why I had the previous slide of the pipeline. So I can show you this pipeline, which without context can be overwhelming. The panel on the left is still the same. You have your theta2, which was our spatial parameters. You generate a bunch of parameter values. You generate a bunch of data. I have transformed them to uniform margins, which is straightforward because these are all hyperexponential. The right panel is where it starts changing a bit. We do learn a mapping still from our neural network takes that inputs the values at the nearest neighbors and the value of the parameter. Since the Vecchia approximation gave us n independent things, we will use n independent networks. It doesn't have to be that way. We can all stack this in one network, where the mapping we learn is from that to the PDF value or the likelihood value for each of those pieces. Like with any neural network, you need a loss function. When we did parameter estimation one I showed earlier, the loss function was just the difference in the parameters. This, we're just going to use the loss function of that basis form representation. Like if this is complicated, just imagine I'm fitting a mixture of normals, where the output is a denorm conditioned on stuff, and the loss function is essentially the log likelihood associated with that. So I have that mapping. I've learned that. How do I use this? Well, we have very off-the-shelf MCMC. We have a Metropolis step. At some point, I've drawn, an estimate of my parameter. I've drawn a sample, and I need to see whether I want to accept or reject this sample. To do that, I need to evaluate the likelihood. Well, at that point, thanks to having drawn that value of theta, I can take all the data I have, transform it all into uniform margins, and take that and my current draw from the distribution through all the neural networks. Each neural network gives me back like a denorm, which is not a denorm, it's a DSPQR, but like an evaluation of the likelihood for that location. So I have all of those. I write it as a product, but obviously, as we all do in MCMC, it's going to be a sum of the log likelihoods that we do. We're just going to add or multiply all of them up. We have now a surrogate of the true likelihood. Now, there are a couple of asterisks here, which hopefully, if I have time and there's interest, I'm happy to discuss. There are two levels of approximation going here. I am approximating the full likelihood with a surrogate version of that, which is like the Vecchia Approximated version, which actually works fantastically in practice. There are several theoretical results for that. And then I'm further approximating it using a neural network. There's a broader discussion to be had about whether, will this come back? Let's come back there. There we go. About like how any errors will propagate through this. But for the time being, this is a way to approximate any intractable likelihood, actually, and as long as you assume a model for it, and do full Bayesian inference on that, should you want. Now, just before I move on, the likelihood itself, even though we do Bayesian inference, you don't have to do it. You have a conditional likelihood. You can just plug it into R and run an optim, and it will give you back the parameter estimates. We just like our Bayesian inference. A couple of simulation studies. The one I want to show here is for the R spatial extremes model. I have a bunch more in the appendix, which are for a GP. And for a Gaussian process, we can get the exact likelihood, the analytical version, so it was easy to interrogate whether the thing was working well. It was. This is for the process mixture model, which is a little bit more complicated. So that's a straight up QQ plot from the neural networks. That site 45 actually corresponds to that second panel I had. That was what we were using for the simulation studies. On the right-hand side is like Bayesian, is posterior distribution of the delta parameter, which I was using, where I mentioned there was there is a regime change at delta equals 0.5. So it's always of interest. Can you correctly at least identify the regime of delta? And in general, we were fairly good at that. The neural network we used for this was very off the shelf. There's nothing fancy going on in the architecture of the deep learning. Of course, you can. More importantly, there's a version of that SPQR thing, which is driven by HMC. So it itself can be a Bayesian neural network. Nothing stopping that, but just with if you're dealing with 100,000 data points, that's, slows things down further. And since we do have Bayesian inference later on, we were okay just sticking with a regular neural network. Now, coming back to the application, you've seen the plot already. This is what we'll be working with. I mentioned in my aims, one of them was to kind of figure out changes over time. So we changed the GV parameter slightly. We made it a slope and intercept thing. But fundamentally, if that mu1 is positive, it means the intensity of extremal streamflow has increased over time. The mu and sigma is not the same as the mu and sigma for normal distribution, but they do have a similar interpretation of a location and scale parameter. Some estimates. A couple of interesting things to note. You'll note that the shape and the xi parameter, which is a tail parameter, are negatively associated. That's a feature, not a bug. That's how the GV distribution is. You will see a lot of positive values on the top right panel, which is that slope term. The only place where it doesn't have positive values very noticeably is on that west coast. But if you look at the intercept of that west coast, that's already so high, that's kind of dominating any change in the last 50 years. Or that's kind of how we interpreted it. Zooming back in, doing this in a Bayesian format allows us to ask statements like this. What's the probability that the slope of that GV distribution has changed over the last 50 years? And we see that for large parts of the country, that is strictly positive. The fact that the values were so high in the central US led to a follow-up study where we modeled this using with precipitation as a covariate, because it's a very storm-prone region, did future forecasts. So this large scale thing allowed us to hone down to different parts of the US down the line. As far as estimates, the only thing that's really of interest is what's highlighted in blue. That delta thing that we care about so much came out to be just about less than 0.5, which is something called asymptotic, which implies something called asymptotic independence, which essentially means, the dependence does die down over space eventually in the tails. The other thing we really, really wanted to do, which was the motivation, can you predict exceedances at multiple locations? So in an extreme talk, everybody would know what this is. But this here, I feel like I need to give a little bit more explanation. So there are three sets of watersheds we looked at. All of them were roughly 10 to 15 watersheds in each plot. It's Colorado, New Mexico, and Oregon. On the top is this quantity, on the top row is this quantity called chi, which measures how fast the dependence is dying down in the tails between any two pairs of locations. And so it's kind of like how a variogram works in terms of interpretation. And on the x-axis of those is the quantile level. And so the dashed line is when we have our posterior estimates, we can generate a bunch of data from our fitted model and get like a empirical value of that. The bounds are also based on that. The bold line, which is a lot more wiggly, is the empirical estimate for the data. And so we're kind of saying whatever our model is fitting, the characteristics we care about, is it correctly capturing that? So this is our validation. So on the top row, yes, it is. More importantly, you'll see that the bounds in each of them are all going to 0, which is consistent with that estimate of less than 0.5 we got. In the bottom panel is like essentially the dependence in the 90th quantile in any pair of locations as distance increases. And again, we see that dependence is eventually going to 0 in most cases. And it's not exactly 0 in some cases because these are all very close to each other, these watersheds. So in some situations, they just don't die out. They remain very dependent on each other. We can also calculate things like joint posterior probabilities. The Colorado sites, I think there were 11 of them, that all exceed their observed 0.9 quantile. And there's an observed 0.9 quantile in 1970 something. There's an observed 0.9 quantile in 2021. We checked their exceedance probability. It was 7.5%. Sorry about that. It was 7.5% back in 72 and is roughly 17% in 2021 by our estimates, which kind of suggests that, the joint exceedance in 2021 is higher than it was. So kind of wrapping up. So glad I'm not keeping people from lunch, that I'll wrap up in time. Extreme value analysis of climate signals, trying to figure out have things changed over time is of growing importance, but the more sophisticated you get with your extremes model, like even if you get a little bit sophisticated, things just spiral out of control in terms of computational cost and just viability. It's not just cost, it's basically impossible to brute force many of these models. The model that we proposed was flexible and expressive and captured some patterns of increasing stream flow, some of which we have validated using future studies. The three interesting things going on here: the flexibility I mentioned, the tractability is due to the Vecchia approximation and our use of that. And as I mentioned, you can use that not only to any spatial process, you can use that to any high dimensional likelihood. And to bring back an interesting thing, if data was gridded, which a lot of people work with gridded data, and that's fine, this problem is simplified even further because you can only have so many configurations of neural networks. If your data is ungridded, as with the stars, this can be a really powerful tool if there is any dependence that you expect between clusters of things. So this is really shines when your data is ungridded. And yeah, it's compatible with wide array of classical inference methods. As I mentioned, you can just run optim on that likelihood. You can use HMC when you're predicting things. You have a lot more machinery available. And the last bullet point is somewhat provocative, right? It's explainable AI. It's only explainable in the sense that you can interrogate everything a lot more than you would if you just directly estimated the parameters. Obviously, caveats to that, this can be sensitive to your choice of model. There are two layers of approximations going on. One more thing is that predictions at new locations is possible, but it is somewhat complicated. It's something I'm already working through, and I'm trying to figure out situations where it works and where it doesn't work. The other part that's kind of interesting, this is somewhat anecdotal, but I'm fairly sure I'm seeing this in multiple situations now. Like we had the SPQR fit, so I had that QQ plot earlier on, which only corresponded to a single neural network at a single location. Even if you have very good fits at every location, the quality of those fits don't always translate to the coverage of your parameters. Like you can have good individual fits, but a bad overall fit is my sense kind of going into this. Why would we kind of care? Because at the end, if we want all of this to wash down, and no pun intended, wash down and somewhat work with policy and affect actual decision making, we do need those uncertainty bands. We do need be able to interrogate our model and our inference really well, because otherwise, we won't have as much trust in the inference that we're getting, and that was our motivation. To tinker only with the smallest possible thing that we need to, and keep the rest of the machinery as rigorous as possible. I'll end with these three things that came out of it. That's what I basically presented, was that entirety of that first paper. We had a follow-up paper, even though the dates look odd, that's just because the first paper took forever. And the package for the density estimation was on CRAN forever until the student who worked on it graduated and his NC State email died, and CRAN was like, nope, this package is now dead. It's still on GitHub, and I think it's a really, really cool tool in general to power any sort of conditional density estimation. I'd love to hear your views, and I'd love to take any questions you have.